So I'm going to get started a couple minutes early here. Usually it's 10 after. But this is a Sackler lecture, special technical lecture. So I'm going to give a slightly longer, not by much because you don't want to hear me, introduction than usual for these. So we're very pleased to have as this year's Sackler, Raymond and Beverly Sackler lecturer, Vicky Kalogera from the University of Northwestern. Vicky did her undergraduate work in Greece in Thessaloniki, is that how you say it?
Yep.
More or less. Okay, good. And then got her PhD at Illinois with Robert Webbing on X-ray binaries, if I remember right. And at some level, she stayed in that area ever since. X-ray binaries are compact objects in a binary. And while she has broadened out and done other things, she's, I think, probably still best known for her work on the origin and evolution of compact binary systems. Okay, and that's she is, in fact, I would say, the leader in the astrophysics segment, or a leader certainly, of the LIGO scientific collaboration, based on the work that she's done in astrophysics, of compact binary systems. So I should say just one or two other things. She did win the Hans Bethe Prize, 2 years ago or so, for work in that area. And a long list of other prizes, which I won't go through, except later tomorrow I probably will go through them all. So. But anyway, to get right to it, she is going to be talking about the Down multi-messenger astrophysics, gravitational wave and light from a binary neutron star merger that is following in the same. Thank you.
Thank you. Hi, everybody. Thanks for coming. So indeed, today I'm going to tell you about this new emerging field of multi-messenger astrophysics driven by gravitational waves and observations, traditional observations in electromagnetic waves. And I will focus most of my talk on this most recent discovery by LIGO and Virgo, gravitational wave detectors of this binary neutron star merger. So this is where we're going to focus. And I'm going to start with this graphic that we prepared at Northwestern with the Chicago skyline. And to scale, we have an actual neutron star. We, of course, don't know exactly the radius of a neutron star. It's uncertain by about 30%. We're trying to constrain the size of a neutron star, but within 20 to 30% accuracy, we can tell that this is about this big compared to the Chicago skyline. And maybe I should learn, compared to the Toronto skyline, how big it is, but I suspect it might be similar. So I'll tell you all about it. We're going to spend the whole talk talking about this one source, binary neutron star. There's a lot to tell, and I'll probably run out of time, as I usually do. But before I get to the binary neutron star, I'm going to make a tiny little detour and remind everybody in the audience that this one binary neutron star I'm going to be talking about in a mass scale of compact objects that might now vary from about 1 solar mass of neutron stars all the way up to tens of solar masses, and covers neutron stars. In this plot, covers neutron stars and black holes. Of course, there's white dwarfs as well at the lower masses. The binary neutron star I'll be talking about is these two compact objects here that merged, and we observe their mergers in both gravitational waves and electromagnetic waves. But before, thank you, we won't need it that dark, and certainly not for all the slides. But before this binary neutron star, LIGO had detected lots, it's amazing to say this. I spent most of my life hoping for one. So we now have a set, we're approaching a dozen, half a dozen, binary black hole mergers. So each triplet here is one merger, two black holes forming a more massive black hole. And just last night, so the blues are gravitational wave detections, and then we're comparing them to black holes that we know mass measurements of through electromagnetic wave observations. And just last night, we announced our latest discovery. Not fanfare, no press releases, no press conferences. It's routine now. This is our latest binary black hole merger discovery. And one of my graduate students, actually, Eve Chase, I'll show you a few photos, led the analysis, a lot of the astrophysical analysis and measurement of these masses, and was a member of the writing team. And I also want to highlight the fact that, because I'm going to be talking a lot about Northwestern and CITA, you're going to see, I want to also highlight our previous binary black hole announcement that came, when was it, Carl? Maybe 2 weeks before our neutron star discovery. This is our previous binary black hole merger, which is the first discovery with 3 gravitational wave detectors, LIGO and Virgo. And Carl here at CETA was both leading the analysis of measuring the masses of this system and doing a lot of the writing of the paper in a collaboration of more than 1,000 people. So contributing greatly for the understanding what this system is telling us, which is the second most massive system compared to the very first one we discovered in 2015. So what I'll tell you a couple more things about this latest discovery. Maybe now we can go back to normal lights. It's a signal to noise ratio of about 13. You can kind of see it visibly in a time frequency plot at Hanford, not so clear at Livingstone, but we can find it with high confidence, and we can measure masses for the individual black holes, for the total final black hole. We can measure how much energy was released and how far away this system was. I won't go into all the details, but the one thing to highlight is that we're expanding the mass range of black holes that we're now finding with gravitational waves. So in a 2-dimensional plane of the 2 masses of the 2 black holes that came together, we can tell that this is the least massive binary we have observed so far. This is the second most, next most, I guess next least massive. Is that? Is that? Thank you. And the chirp mass, which is the thing we measure the best with gravitational waves, is definitely the lowest. This is the second least massive. This is the total mass of about 19 solar masses. And for those who are interested and are a bit of connoisseurs, I don't have time to expand on the binary black holes today. We can measure a bit of a spin. The tilt is more likely closer to being aligned with the orbital angular momentum axis of the binary, but in terms of the magnitude of the spin is probably relatively small, although we cannot fully exclude high spins as well. And again, I'm showing these plots for the people who are more familiar with our binary black hole observations, and I don't have time to go into the details. So the rest of the talk is going to focus on this binary neutron star, which is the second most significant discovery from LIGO Virgo. And I will tell you the story of the multi-messenger observation. So I'm going to try and pack in this talk the gravitational wave discovery, the discovery in gamma rays, how 12 hours later or so, our electromagnetic colleagues, helped by localization from gravitational waves, discovered the first optical source and the host galaxy. And then eventually that led to a multi-wavelength electromagnetic campaign that went from gamma rays first into optical next, infrared, ultraviolet was the next detection, eventually X-rays and radio joined. And I'll try and cover all of this in the next hour or so. But I have to tell you that for the gravitational wave analysis, I speak on behalf of a massive collaboration of more than 1,000 people. So when I say I mean we. Sometimes we, 1,000 people of science and engineers. None of this would be possible without our amazing instrumentation people scientists and engineers who created these, who built these instruments that can make these spectacular measurements, the most accurate a human being has ever made. Often when I say I will mean my group at Northwestern. Often when I say I mean you know, CETA people here that I'll try to highlight. Keep in mind, this is an enormous effort that has lasted for many, many decades and has led to these famous moments that we all brag about, but it's been an amazing effort over many decades of many people. So here's the CETA group. Harold hasn't been around lately, but you know the faces: Aaron, Katerina, Carl, Heather, they're all in the room. I don't know if Prayush is, I don't know if he's in the room, and I'm not sure of the name here. I'm going to highlight my group next, but I want to say that Aaron and, I should say that Carl, I already said that he was a heavy contributor to the triple detection of the binary black hole, but Aaron, Katerina, Carl, and Heather were directly involved in the binary neutron star discovery. Heather works with the pipeline that actually found the signal. Kip Cannon wrote the pipeline that found the signal. Aaron, Carl, and Katerina all did a lot of the parameter estimation, we say, extracting. Once you have the signal, you want to measure the masses, the spin, the size of the neutron stars, et cetera. So they were directly involved in many of these. And I'll try to highlight their work along the way. And then you're going to allow me to brag about my group and other people at Northwestern. We actually had a, partly luck, partly my doing, I will say. The last 2 years, we expanded the group at Northwestern, and we have been lucky to attract electromagnetic observers who do time domain astronomy. So when this system arrived, we had 2 spectacular young faculty at Northwestern. When Fei Fong had joined Northwestern 1 month before the discovery. In fact, she's still a Hubble Fellow officially. And Raffaella Margutti had joined a year before. And as an institution, we are the only institution in the whole collaboration who has, in the whole, actually, astronomy community that has leadership role in both sides of the discovery. And I can say this with a straight face. And yes, this includes Caltech and MIT and whoever else you want to ask me about. Leadership position, not just a position in both sides. My group on the LIGO side is here, Shane Larson and other faculty. Both of us were members of the writing teams of the 2 flagship papers for the collaboration. I'll come back to that. Chris Panko, postdoc in my group, chaired the writing team and led the analysis for our kilonova collaboration paper. Eve Chase was busy working on the paper that announced the binary black hole last night, but also worked on cleaning up, reviewing the analysis for cleaning up the data for the binary neutron star. Scott did review work of codes and papers for all the papers effectively. A graduate student with me. Mike Zevin was the first graduate student ever to be allowed to chair a writing team for a collaboration paper for our astrophysics progenitor analysis. And Chase Kimball, first year graduate student, worked on that. So I'm all very proud for them. And we also have a faculty who leads 3rd generation technology for gravitational wave detectors. And then these 4 are all electromagnetic observers. They're not my group by any means. And they were led by these 2 new professors at Northwestern who had a lot to do with leading the first discoveries hours after the gravitational wave discovery. So I'm going to tell you, I'm going to run out of time, but this changed our lives. And it's too soon to forget. So I'm going to tell you all about it. The first email I can recognize was this one-liner from a colleague, young assistant professor at MIT, who just sent it around, pointed out this ID event, and said, of interest. August 17th, 7:55 a.m. The next email, 1 minute later, GST-LAL, the pipeline built by Kip Cannon here at CETA. Heather Fong helped a lot with that, found a very significant false alarm rate less than 1 per 1,000 years. That was the early estimate. It became more significant with more analysis. Binary neutron star trigger within 2 seconds of a gamma-ray burst. The gamma-ray burst detection was independent of the gravitational waves with a beautiful track through the omega scan, the time frequency plot I'll show you again. We're on the EM follow-up call. We'd like to send an alert immediately. Vivian Raymond, a graduate student of mine from some years back, a little later writes to Aaron here and Carl here and Soichiro, who were the PE rotas. So every week we had parameter estimation people on duty to follow up on triggers. So he writes to them. So Vivian was my graduate student. Now he just started the faculty at Cardiff. He's the chair of the parameter estimation group. The co-chairs are actually both my graduate students of that group, Vivian and Ben Farr. Vivian writes, please do this and this and that. I will not go through the details. His PS is so underwhelming. Wow, what a time. I have more exclamation mark in my tone than he has in his email. I was on vacation, my 1 week of family vacation. 3 days before we had detected a binary black hole, the triple detector black hole. That screwed up my family vacation. 3 days later, we get the binary neutron star. That really screwed up my family vacation. So I had an exchange of emails where I say to my graduate students that they need to be alert. They were all over the place. Scotty was in Europe. Eve was visiting her parents. Chris was at a conference somewhere in California. I was in Idaho trying to have a vacation before the eclipse, which was the 21st. And I tell them all, Chris will be bringing the data of the BNS detection to Quest, our high-performance computing cluster at Northwestern. At some point, he may ask you, Mike Zevin, Eve, and Scotty, to run on them with inclination frozen on face-on, face-off, which is something Katerina also did independently at some point. This is life-changing, which was my way. I wasn't trying to be philosophical. I was trying to tell them, drop everything you're doing. This is what we're doing. OK. When we went on announcement, October 16th, we had 6 papers, collaboration papers, accepted. 2 flagship papers, multi-messenger. I'll come back to this, almost killed me. I was on the writing team. My colleague, faculty on the writing team, kilonova paper chaired, analysis led, and paper writing led by my postdoc. Analysis led, paper writing led, chaired by my graduate student. There is no other group in the collaboration with this leadership. Electromagnetic observations, there were 3 teams that discovered the host galaxy independently within minutes of each other. SWAP telescope led by Ryan Foley at Santa Cruz, 8:06, I received the circular that announces the host galaxy. 8:16, I receive another circular from the DCAM team. Ido Berger is the PI. Ryan Chornock was the one who found the image with the source. DLT-40 from Arizona, Dave Sand and Stefano Valenti, 2 co-Is, 8:42. These are the first 3 teams co-discovered. By the way, there's an interesting something for those astronomers here. I can't resist saying this. Ido Berger, the PI of the second team, sent the circular announcing this discovery from the first team. Ask me over coffee or dinner. So So the faculty at Northwestern, the two faculty we had just hired, were part of the DCAM team. So I'll focus on the DCAM team results, but they reproduce many of the other results. The DCAM team, on the day of the announcement, had 9 papers out. 3 were led by these two faculty at Northwestern. Okay, enough bragging, time to get to the science, if my slides collaborate. So I'll start with the gravitational wave discovery. And this is what we saw at about 8 a.m., and I can't remember which time zone. I was in the West. Woke up to start. I had planned this perfect spa day. My husband was taking the kids out hiking. I was going to be alone for the whole day. This happened. You see it very nicely here, about 30 seconds plotted here that you can see it by eye, but the signal is about 150 seconds long. Nothing in Virgo. We'll come back to this. But there was a glitch, really, a real glitch. In Livingstone, where the signal is clearly visible by eye, so the loudest, here it is the signal, there was a giant noise signal on top of it. So that caused us trouble for quite some time. The signal to noise ratio, if you clean the data from this glitch, is the loudest signal we've ever gotten in LIGO. Signal to noise ratio of 30 plus is unheard of. You know, 2 years ago, if you told me our first BNS was going to be at SNR of 30, I would tell you, you're crazy. Don't pull my leg. This will never happen. Our first binary black hole was 23. So we realized we have a glitch. A lot of people did a lot of work to figure out what to do with this. But we were able to remove it because it doesn't look like anything like a chirp signal. So then we could get this. Independently, we could get this, put the two together. We'll come back on the Virgo. Actually, it's right here. I'll tell you in a minute what happened with Virgo. But with just the two LIGO detections, we could tell that the source on the sky was somewhere in the light green thing here or here. Virgo saw nothing, but Virgo was operating. And 3 days before, we knew Virgo had detected a binary black hole. And it was working beautifully and had seen a binary black hole exactly as expected. And there was nothing wrong with Virgo. We also knew from LIGO that this source was not just there in the sky and booming at SNR of 32, but it was at a tiny distance away from us. For the astronomers, only 40 megaparsecs. So we knew how sensitive Virgo was, and we knew that if the source is at 40 megaparsecs, Virgo had to see it. The only way Virgo could have zero signal was if the source were at the blind spot of the detector. And that's exactly what was going on. So blind spot, what do we mean? Very quickly, as you're driving and you're looking at your rear view mirror, I'll use a public outreach analogy that I'll use tomorrow as well. You have a blind spot in your rear view mirror. And when a car is in the blind spot, it's at a very particular position. So you can localize, if you could see it in the blind spot, you can localize that car very well. Okay? So the fact that Virgo didn't see, and I won't go back because it will take time to load that slide with a glitch, is very slow. The fact that Virgo saw nothing meant it was in the blind spot of Virgo, and therefore we could localize the source very well, and therefore we could tell with Virgo now, non-detection, very small SNR detection of only 2, we could tell it was right there. And that triggered the electromagnetic community. Now, Fermi GBM is the gamma-ray detector. The gamma-ray detection had happened, and their localization was this. That alone was not a first. So gamma ray detectors had seen lots of these events. With a sky localization of these, optical observers never followed up those gamma ray events. Okay, this was too big. The gamma ray flux was too little. Nobody was bothering to do anything. But the gravitational wave detection coinciding with the gamma ray detection and a tiny little banana on the sky. Literally, this is like a banana at arm's length on the sky. That triggered them to go and search that tiny little area. OK, back from the gravitational wave data, we could easily measure masses. We could assume different things about the spins of the neutron stars. If they are spins like the spins we see in double neutron stars from pulsar observations, we get a range of masses clearly within the neutron star mass regime. If we are being a little more agnostic about the spins, we get some higher, broader range of masses, but clearly not black hole masses. What else is of significance? The distance, clearly 40 solar masses. And then we'll come back to these lambda parameters. So you can see the masses are tighter, restricted for the low spins and broader for the high spins. Either way, they're clearly neutron stars. Unless, if you only have gravitational waves, maybe they are black holes of very low masses. Formally speaking, we cannot exclude it from gravitational waves alone. All right. So this is where we are. These are other neutron stars from electromagnetic observations. So consistent with neutron stars. The signal for binary neutron stars, because of their low masses, is very long. So we have, these are all the black holes. And last night, Ben Farr, my ex-student also, added last night's gravitational wave binary black hole. We have 6 binary black holes so far announced. So far announced. But the signal in binary neutron stars, it's much, much longer. Okay? So we have lots of data on the binary neutron star, tiny lengthwise in time for the binary black holes. Now, with neutron stars, we can do one thing we cannot do with black holes. With neutron stars, we can measure radii. Now, it's tough because the final merger of the 2 neutron stars happens at frequencies that are too high for the LIGO detectors to see. Okay, so we don't see the final merger of the compact objects. With black holes, we see the final merger. With neutron stars, it happens at, we don't know exactly, we don't see it, but it happens at about 16, correct me, I should have said this in the beginning. The young LIGO people should correct me in here. Isn't it? Are waveforms telling us 1600 hertz? No, it's wrong. What am I saying? Oh, you don't remember either. It's not that I'm wrong. I remember 1600 hertz. OK. So it's beyond our sensitivity. But the signatures of the fact that neutron stars have an actual surface and a 3-dimensional existence, those signatures become detectable at about 500 hertz. And that is within the frequency band of the LIGO detectors. So Katerina has worked, for example, and Aaron, and am I missing any citizen here? Aaron worked on these runs? No, OK. Aaron worked on exactly this, constraining the size of the neutron stars based on the gravitational wave signal. So I will not go into the details of defining this lambda parameter, because then I will really run out of time. But I'm happy to answer questions on this. But the point is we have a parameter that modifies the gravitational waveform as a function of frequency. And these modifications show up at about 500 hertz and above. And you're trying to match your waveform with your data, and you get maximum likelihood at some point, and that allows you to not exactly measure this lambda parameter, but set at least an upper limit on lambda. And that allows you to set an upper limit on the radius. Depending on the spin you assume for your neutron stars, low spin as before or high spin, you set different upper limits on these lambda parameters for one neutron star and the second neutron star in the system. These upper limits are these dashed lines, okay? And then the different, and I should say this dashed line is 90 percentile upper limit, 50 percentile upper limit, and the same here. And the other lines we're seeing here are predictions for how big neutron stars should be based on different nuclear physics equations of state. So there are equations of state like this MS1 equation of state or MS1b, and the same here, that are now being excluded. The upper limit sits here. I hope this is not me, okay, because it could be. These two are excluded by our upper limits from this one system at 90 percentile, actually at higher, in terms of this being a representation of reality. So we're excluding equations of state. Now the question is, nobody knows what these lambda values mean. Okay, so here's the real piece of information. These are different equations of state. There's a gazillion of them based off nuclear physics understanding. It includes even quark stars, etc. The two I showed you that are being clearly excluded, MS1 and MS1b. These are these two. And basically, we can say with confidence that we can exclude radii higher than 14 kilometers per second. What am I saying? That's kicks. 14 kilometers. We're going to come to kicks maybe eventually. All right, so we cannot exclude smaller radii. But Carl just showed me, Katerina, something before I walked in I can't talk about. So that's where we are for now. All right, now one statement or a couple about rates. Something I got sick of at some point, but something I spent my junior faculty years doing. Basically predicting lots and lots of different rates for what LIGO will see one day. I did it in many different ways, assessing uncertainties, deriving fancy statistical methods for how we should make predictions, deriving errors, deriving confidence on the errors, blah, 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 etc. I got sick of it at some point. I stopped working on errors, on rates. It turns out there was something okay back then from what I was doing. So in 2010, we wrote with a collaboration a review paper that put all the rates together, not just my predictions, but everybody's predictions. But at the time, the double neutron star rate predictions, the best predictions were coming from taking the double neutron stars we knew from radio pulsars, from radio pulsar astronomy, and using those to understand all the selection effects in great detail and figuring out what's the rate then that LIGO should, that mergers are happening in the universe and eventually predicting what LIGO should see. So in terms of the universe merger rate, density, so per cubic megaparsec, per event mergers per million year, per cubic megaparsec, we, based on work I had done in 2004, we had concluded that there is a realistic prediction of 1 in these units, a very pessimistic prediction of 2 orders of magnitude lower, and a reasonably high prediction, optimistic prediction of 10, And then the maximum you really could not cross, because that's basically connects to the supernova rate of 50. And then the rest is binary black holes, etc. This one system allows us to make a measurement of the rate. And this is the rate with the error bars we measured. 1.54, plus or minus some big numbers right now. But not that big, not down to this level big, okay? So, so we're at about 1.5, but maybe we're as high as 5, maybe as low as 0.3. So at least I didn't completely waste my time back then. In terms of our predictions, we wrote back, when was it? Yes, so not that long ago. About a year ago, at the end of our first observing run, we had no binary neutron star detections. And we said, OK, when we run our second observing run, we may have an upper limit set for binary neutron star merger rates. And our upper limit is going to be somewhere in this green band. Right now, our measurement is between the two red bands. And you can see already that it excludes some models, OK, or here. What we expect from our experience with binary black holes, our rate predictions from the very first 1 event to the 6 events has dropped down by an order of magnitude, but it has stayed consistent. Okay, it hasn't shifted from our first rate prediction measurement. So what I would expect is that this will keep shrinking. It doesn't have to go to the center. It might shrink this way or that way, whatever. So we'll see where that goes. All right, so where am I time-wise? I don't see a clock. That's dangerous if I don't see a clock. Ah.
But you go to the hour.
OK. So 15 minutes for the electromagnetic part. So this is now not my work. So I'm just going to give you not my work or the gravitation or the LIGO Virgo collaboration's work. But I want to give you a little bit about what we learned from the binary neutron star in terms of the electromagnetic emission. Well, the first thing we learned is that the merger we saw in gravitational waves, it's not two low mass black holes. Okay? For sure, one of them has to be a neutron star because we got electromagnetic waves. The second thing we learned is that it is associated with a short duration gamma-ray burst. And again, it's going to be very hard for me to give you the full picture, but hopefully most of you have heard of gamma-ray bursts. They've been known to astronomers since the late 60s. In the early 90s, we concluded they come in two varieties, the short and the long ones. In the late 90s, we figured out that the long gamma-ray bursts are produced by massive stars collapsing into and producing supernovae. And for short gamma-ray bursts, Paczynski, was it 86? Yes. Told us that short gamma-ray bursts should be mergers of neutron stars, and nobody believed him. Paczynski at Bodan at Princeton. And in fact, some people made fun of him. And it turns out he's right. He was right. And then other astrophysicists strengthened that prediction. And from 86 to now, he now, 30 years later, has been proven right. So we got the short gamma-ray burst associated with a gravitational wave signal that clearly says two low-mass objects, one of them for sure a neutron star, probably the other one too, similar mass, are giving a short gamma-ray burst. Here's the actual data. This is our gravitational wave chirp. It ends. Less than 2 seconds later, there's an actual burst in gamma rays. It's clearly seen here in Fermi GBM. And it dies off less than 2 seconds later. And below 2 seconds is the classification for short gamma-ray bursts. Okay, so If it were chance coincidence, this is the probability for chance coincidence for both spatial on the sky and temporal. There is a little but in the story. If you look at the redshift distribution of short and long gamma-ray bursts, and the assumed, if you take the flux and you know how far away these bursts are happening, then you can calculate what is the isotropic energy they must be emitting. You put them on this plane. Blue dots are long gamma-ray bursts. They're supernovae, nothing to do with us. Short gamma-ray bursts are the few points for which we have redshifts. We have many more short gamma-ray bursts, but not many with redshifts. You see the orange points. You do the same thing for this one event. It's down here. This is 4 or 5 orders of magnitude. Okay, so it's a very unusual short gamma-ray burst. You look at it in different ways. In the split between short and long, this is where it sits. It's classified at 73% a short gamma-ray burst, but 26% a long gamma-ray burst. But we know it's a merger. It's not a supernova. In this plot, classic also classification of duration and spectral hardness, it's really at the boundary between short and long. And then the other weirdness is that it's not a single peak gamma-ray burst. It has a narrow peak, goes down in flux in gamma rays, and then a secondary peak, all within 2 seconds. So there is no question, it's not a vanilla short gamma-ray burst. Is it all short gamma-ray bursts are double neutron stars? Is this an unusual one? We still don't know. So on the one hand, we kind of say we solved the short gamma-ray burst mystery. On the other hand, maybe only this one is a binary neutron star merger. So we'll have to wait for more. There are all kinds of theories developing. That has to do with what is our viewing angle. Maybe the luminosity in gamma rays is low because we're not looking down the jet, we're looking on the side. Maybe it's not a uniform jet. Maybe there's a cocoon, etc. Okay, so lots of questions. Now let's move to optical. 12 hours later, when we reported first a bigger location, and eventually the small location. The optical telescopes knew where to look, but it was in the southern hemisphere. The gravitational wave and gamma-ray burst detections happened at 8 a.m. Eastern time. So they had to wait for the optical. They knew where to look. It was southern sky. They had to wait until it becomes night. So they could prepare using Chilean telescopes. But the problem was that the source was going to be visible at night from the south, but it was very close to the sun. So it was going to set right after the sun. So there was about a 2-hour window for catching potentially the sky area they had to look, but the sky area was going to set right after the sun. So the first team that got the first image by timestamp and announcing the circular was the SWAP team led by Ryan Foley. And they saw this booming optical source right there, away, not far away actually, but in the optical it looks like it is in the outskirts, while it's not really. And 20 days earlier, another team had accidentally taken an image of this galaxy, and clearly there's nothing there. Okay? So this is the first optical image. Now, I talked to you earlier about 3 teams that announced within half an hour their independent discoveries. 1, SWAP, DCAM, DLT40. There's 3 other teams that also took images before the first circular came out. So they also have a co-discovery independently, since they took data before the first circular. So we have 6 teams that were highlighted in this massive multi-messenger astronomy paper we wrote, led by the LBC. I was a member of the writing team. Almost 4,000 authors, 950 institutions, 59 research teams, one of them being the LIGO collaboration, 1,000 people. It was an upJ letters paper. Just the authors and their institutions was 24 pages. The full paper was 59. And we were a team of 11 people writing the paper, telling the story of the multi-messenger detection. Another paper we wrote as a collaboration is the fact that this one source, single source, enables a brand new way of measuring H0. New systematics. Welcome to gravitational wave cosmology. Now, this was, of course, as an idea, was proposed by Bernard Schutz, also in '86. And Bernard was involved on the writing team of this historic paper on H0. But on August 18th, Will Farr, who now is the faculty at Birmingham, postdoc in my group some years back, sends this email. So I wrote back. Right after DCAM sent the circular, I wrote, it was an AM my local time. It was probably AM, 2:20 AM his local time, Will's local time in Birmingham. DCAM has the potential afterglow counterpart in host galaxy, one line. Then he wakes up at his local time and says, which gives H0, this is how we communicate. There's no DRX, it's like we're on the phone or something, which gives H0 78 plus or minus 18, 59 to 115. When combined with Carl's, this Carl, latest PE run, distance estimate, posterior on H0 attached, here it is, full calculation at some Git repository. Wow. Okay, now this value didn't hold because we improved our PE runs, our systematics, etc. The real result is in the paper, and here it is. And this is the posterior on H0 from gravitational waves from one source. It's like having a one type 1a supernova. Okay, one. The 2 results we have the best right now are in contention from Planck and from Adam Rees's sample of type 1As. They're not in agreement. Of course, our one sample, one source posterior is kind of wide. Okay, agrees with both. But you can see where we're going. And the systematics are completely different. There's the degeneracy with our viewing angle of the binary. Okay. Kilonova paper, we can use just gravitational waves to make predictions for how bright and what the optical curve should be for the kilonova. And progenitor paper that we developed with Mike Zevin, my graduate student, can tell us, and I won't go into any details, can tell us something about what happened at the supernova explosion for the system. Where do I want to point? Because I'm not going to describe all of this. We can get some loose upper limit on how much the second neutron star was kicked. The important result is actually here, is that this upper limit is completely insensitive to the star formation history of the galaxy, as long as the star formation age, as long as the stellar age is older than 1 gigayear. And the punchline result is in the fact that all these gazillion of curves are on top of each other. Okay, so I won't have time to explain. Okay. All right. So You must have heard something about, I told you about the host galaxy, but you must have heard something about gold production. So let me tell you a little bit about that. The point is that we had observations beyond gamma rays in optical, near infrared. That tells us something about gold. X-rays and radio tells us something about the relativistic outflow out of this. So I'll try to put this together in a visual sense. The merger happens in the center of this thing. It produces a smaller scale isotropic component of emission where all the UV optical infrared is expected to come out, rather isotropic, and where we expect the heavy elements are being produced. And then we have a highly relativistic outflow that probably come out in jets. That's where the gamma rays are being produced, as well the X-rays and radio. Okay? All right, we talked about the optical, so I'm going to skip that. The heavy elements have been hypothesized of being produced in merging neutron stars for decades now. We know that stars regularly don't form anything beyond iron, and that heavier elements get formed in situations where you can have, for example, two neutron stars merging, or core collapse supernovae, where you can get lots of neutrons to come together and eventually form these heavier nuclei, where you can get things with more neutrons in their nuclei. In that process, people have wondered, how would this look like in electromagnetic emission? So the emission that had been predicted was called macronova originally and kilonova more commonly now. And some of the latest models come from Brian Metzger at Columbia and Dan Kaysen at Berkeley. And long story short is the following, that initially the emission was predicted to be red. Then I think it was Brian who said, wait, there may be blue emission. And then Dan Kaysen said, wait, it may be possible that you start with blue and it evolves in red. And this is the latest sort of theoretical predictions from papers before the discovery that shows exactly this. 1.5 days after the merger, you have a strong blue component. 7 days later, your blue component has disappeared. You have a strong red component. This is as a function of wavelength, longer wavelengths, red components. Okay? So that was what was predicted. This is what was observed. I mean, if this is not a triumph for theorists, I don't know what it is. Merger rates, gamma-ray bursts, short gamma-ray bursts, and now the kilonova emission. So plus 1.5 days, actual data. High blue component. By 10 days, you mainly have red emission in actual observed flux. How do you get that? It has to do with what heavy elements you have formed initially. You don't have lanthanides. Later, you're lanthanide rich. This is data from the DCAM team that connects to Northwestern, but this is all independent. All the teams who looked at the source found exactly the same thing. And at the end, look at this. It's not perfect, but you know, for independent theoretical predictions before the observations, it's as good as it gets. Spectrum observed. Theoretical prediction not tuned to this particular source. Okay? And it gives you, that's from Dan Kaysen. It's a red kilonova model at 4.5 days. All right, so optical discovery first. 13.7 hours, people looked at radio, multiple groups, saw nothing. 1.5 days, they got spectra for the first time. That was the second night. And the spectra I just showed you already. 2.5 days later, they tried to look in X-rays, and they got nothing. So there was an upper limit. That was a surprise. Short gamma-ray bursts in 2.5 days normally show X-rays. Bizarre. 9 days, first detection came from Nora Troya. 15 days, the detection persisted. That's Margutti from Northwestern. And the next day or hours later, Daryl Haggard from McGill, and I just happened to be the token theorist in the team. I did nothing, co-wrote the proposal. We got again a detection. And the source became brighter and brighter. Bizarre. So X-ray brightening is significant. 9 to 15 days, X-rays came into view. Radio came into view 16 days later. Let me skip this. The point is the X-rays with Chandra are brightening. Why is this happening? This is not normal. Normal short gamma-ray bursts, the X-ray luminosity goes down with time, starts early and goes down. This got delayed and goes up. Well, it supports the fact that we're not looking down the jet. Okay, we're looking offside. The jet is narrow in the beginning, highly relativistic. You're looking here, you see nothing. Later, the jet decelerates, broadens the beam, and eventually you get your X-rays. So that might make sense. So normal short gamma-ray bursts that we can see far away, we look at them on beam. This one close by, we look at it off beam. All right, I'm about to close. I'll tell you about the future. This is where we are today. Last night, we had to rush and add another system. This will get populated, will keep getting populated. The detectors are down for a whole year. We can sleep. But they're going to come up in about a year, and they're going to be more sensitive. And we expect a binary black hole per week, a binary neutron star per month. And we cannot handle it. So this is where we are now in terms of where advanced LIGO and Virgo are supposed to be. One detector, Livingston, at 100 megaparsec sensitivity. Hanford went down. It used to be up there. No, it used to be at 80. But there was a big earthquake in Montana. Yes. And we went down in sensitivity. Virgo was running for 1 month and got a binary black hole and didn't get a binary neutron star, but was very useful. And it's down there. By design sensitivity, around 2020, maybe a year later, we're supposed to be up there with Virgo and up there with LIGO. Wow. The instrumentation people can do it. They've proven it. How are we going to cope? We're going to be seeing binary black holes of this kind of mass, if they exist, but 20 total mass. 40, 60, we know they exist. This is the September event. We're going to be seeing them out to, this is design sensitivity, out to 10 gigaparsecs. Okay? This is not a dream anymore. For this, last slide. For this one source, so many firsts. First multi-messenger, including gravitational waves. There is another multi-messenger, of course, 87A supernova, neutrinos and electromagnetic waves. First double neutron star merger discovered. First double neutron star merger associated with a short gamma-ray burst, even though it's not vanilla. First kilonova associated with a double neutron star merger. And the first clear evidence for a relativistic outflow from a double neutron star. We're very happy and exhausted. Thank you.
escape, get it out. All right, there was a question in the back there.
Hugely interesting talk. So my question is, there is a periodical table which will show different
sources.
Yeah, and how do you? I can see some of these little block has a mix of two different colors. How do you determine the fraction?
Oh, the fraction. It's not all well established, and it's meant to be. There's a lot of uncertainty there, but for example, we kind of know how many low mass stars are dying within the lifetime of the galaxy, et cetera, and extrapolate to the universe. So that's how, and we think we know how much is being produced based on theoretical models. So I would take these fractions in the boxes of what is merging neutron stars versus dying low mass stars with a huge grain of salt. Okay, so it's more. This is, and so I don't want to. Probably this is a graphic designer, and it's not her fault. So I don't believe in detail these particular fractions here, because honestly, even with merging neutron stars, we don't know how much each merging neutron star is forming. Now, for the first time, we have measurements for how much emission we got from this. But even in this particular source, if you look at the spectra, there's broad features, but there's no individual lines we can identify. The ejecta are moving with high velocities, and we cannot tell, oh, we have so much mass of this element and so much mass of this element. So really, we can't tell how much of individual elements we are forming.
Also, it's not ruled out that core collapse contributes significantly.
That's true, yeah. So, maybe this is a little too hand-wavy and a little misleading, maybe.
There's some of these little blocks which the dying low mass star just occupy the lower right corner. So I feel, well, that's
here.
People have confidence that
No, she's just said they don't have confidence.
They don't. There's exactly. It's a possible source, and I wouldn't bet anything on whether it's down here or up there, etc.
Even as Chris said, the R process originally people thought it could come from core collapse supernova, and it's not clearly not impossible that some of that is wrong.
Yeah.
It's probably not the major part, I guess, what we could probably conclude.
Yeah.
Other questions? Yeah, here.
Wondering, are there models or simulations on the geometry of the combining neutron stars? Do they crumble or deform, or do they get stuck into a barbell and affecting the observation?
Yeah, so I mean, there's many different groups who study the hydrodynamics and MHD of the two neutron stars coming together. And they're, right now, the latest I remember is that maybe you can form, it used to be, so maybe you can form a bar for a short amount of time, and maybe you can get some gravitational waves right at the merger from sustaining along for a few dynamical timescales a bar. But eventually, probably you're forming a hypermassive neutron star that may be able to survive through high rotation and maybe will eventually collapse into a black hole. None of this physics is actually tractable, or we cannot probe this physics with the LIGO detectors right now, because all of this is happening at higher frequencies where we don't have that kind of sensitivity. So the other thing you asked is whether we can, it used to be that there was a notion that maybe very high rotation will maybe cause more breakup and have, I don't know if there was ever in simulations multiple, breakup into multiple remnants. But I don't think that's viable anymore.
Half-baked.
Half-baked ideas of
models that involve that.
Yeah, but I don't think those are viable anymore. But a bar, some kind of a bar sustained for some dynamical timescales, that I think might still happen, especially if there is magnetic support at some level, I think. But experimentally and observationally, we can't probe this yet.
So what add a little bit? Go ahead.
The model, the waveform model, you probe in your demonstration. So how to justify the systematic uncertainties as well as the uncertainties in the redshift?
In the uncertainty, so okay, in the distance. So the distance measurement, honestly, is coming more from the early part of the waveform. So I said the waveform in the band, the LIGO band, lasts for 150 seconds. And the distance we measure extremely well from the early part of the waveform, where we are at point mass still post-Newtonian part of the waveform, which is extremely valid, and we accumulate a lot of signal-to-noise ratio, and that's where we measure our chirp mass and distance. Now, when we go to the higher frequencies, we start moving away from the post-Newtonian approximation, and there we have significant systematics. The spins start becoming important. That's why our mass measurements are spin-dependent. And the tidal effects start becoming important. And there, whatever waveform we can get our hands on, we try, and we assess our systematics. And it's hard to assess the full systematics because if there is physics there that our waveforms are not covering, then it's hard to quantify our systematics. So there is a limitation based on what is the waveforms we have been able to produce from numerical relativity, etc.
Okay, this kind of two questions related. You mentioned that the X-ray behavior is strange and can be explained by that the usual behavior is collected from looking on the jet, but this one is offset. Is that consistent with the selective bias analysis on that one? Also, is the fact that we're viewing from the side has anything to do with the fact that gamma ray is weaker than?
Yes. So yes to both questions. So first of all, it is a selection bias. So if we take that sort of hypothesis at face value, if you're looking off axis, your gamma rays are faint. And that means you can't see these kinds of faint short gamma ray bursts far away. So the ones we see at large numbers are the ones that you can see far away, and you can only see them if you're looking down the jet. Otherwise, they're too faint to see. So that's a selection bias, right? And yes, as you said, your second part of the question, the low flux, the low energy, once you know the distance in gamma rays, is associated with looking off axis. What I don't know fully quantitatively, well, I know part of the answer. So one needs to do the following analysis, and I don't know if the gamma ray people have done it fully or not. They have a sample of Fermi short gamma ray bursts. Based on fluence, without knowing the distance, they know that this event was at 58th percentile in their distribution. How does that translate now that you know the distance? Can you say something about the rest of the population for which you don't know the distance? Is it that the low fluence event, is it consistent with a, I don't know, constant short gamma ray burst rate, constant in volume? And does it make sense if you have a random orientation to the jet? Does it make sense that this is our distribution of fluencies, blah, blah, blah? Does the statistics hang? Or is there something weird in our statistics of low fluence events that somehow there is a subpopulation of low fluence events? And I don't know the answer, and I don't have access to the gamma. Well, actually, the Fermi data are public. But anyhow, I don't have I'm not the one to be doing this analysis, at least not right now. But I think there's interesting questions that can be explored now.
Okay, last question, John.
Yeah, so this is a question about sort of the event rates and proximity of the neutron star. So let's say, I estimate it's like maybe 1 in 1,000 or so that these would happen within the galaxy in our lifetime. So let's say a neutron star meteor happened in kiloparsecs away or in the local group.
Yeah.
Would that like blow away LIGO, or in terms of
Would it knock the
the
mirrors
signal to noise would it be so incredibly high?
Oh, this was 40 megaparsec. If it was 40 kiloparsecs, so at the edge of our galaxy, a little bit further. So 40 kiloparsecs would be Magellanic Cloud. It would be 1,000. I'm sorry?
It might knock LIGO out a lot. I'm not sure. It would be extraordinary.
It would be 1,000 times higher SNR. It would knock LIGO off lock. It would kind of mess up the detector.
Major disaster.
No, but let's say you can measure something like that.
Yeah, but rate-wise, if it were 1,000 times closer, it would be, rate-wise, it would be 1 billion times less likely. So.
Well, in the local group. So let's say it was in, let's say there's a, just trying to figure out the volume, say.
But by volume, you know, if it's 1,000 times closer, it's 1 billion times smaller volume.
So the question is, what's the closest one we
Right?
see in the next 10 years?
Not thinking straight, maybe. So I think it's pretty unlikely to get something this close. So.
All right, well, I think we should probably stop there. So let's thank Vicky again.
Thank you.